This is a GCSE lesson on specific latent heat. So let's start with our key terms. We have specific latent heat of fusion, specific latent heat of vaporization, and internal energy. Before we start, let's look at some quick questions. We have state the SI units of mass, state the SI units of energy, and state the boiling point of water. And finally consider if it takes 10 minutes to heat liquid ethanol to boiling point, which is roughly 78 degrees C, what temperature will it be if you heat it for another 10 minutes? So here's a glossary of our key terms. We have specific latent heat, which is the energy required to change the state of 1 kilogram of material. So that means from solid to liquid or from liquid to gas. And specific latent heat of fusion is the energy required to melt 1 kilogram of material. And specific latent heat of vaporization is the energy required to vaporize. That means to turn from liquid into gas, 1 kilogram of material. And finally, internal energy. This is the sum of all kinetic and potential energies of all the particles in an object. So let's look at what happens when we heat something up. So when you apply heat, here's a graph showing us how if we're constantly heating something, as time moves on, the temperature increases. But you'll notice a very important thing. If you heat a solid, its temperature will increase until it starts to melt. But if you keep heating it, then it will stay the same temperature until all of it has melted. This is because at the melting point, the energy being added doesn't go into making the particles move faster, but rather goes into breaking those bonds that are holding the atoms in fixed positions. So if we look at a similar graph, if we increase the internal energy of material, again we could do this by heating, the thermal energy will not always increase. So the total energy in a material is the sum of the kinetic and potential energies of all the particles. So that's the total amount of energy, that's internal energy. Now when you increase the internal energy of material, that doesn't always increase the thermal energy. That's because thermal energy is due to the vibration and movement of the particles. However, when something is melting, the particles don't vibrate or move faster. That energy is needed to break the bonds holding them in fixed positions. Or in the case of boiling, that energy is needed to break those bonds that are holding the particles close together. So remember that solids have particles vibrating around fixed positions. When it melts, they're no longer stuck in fixed positions. When it's a liquid, they can move past one another. So we've broken bonds, which requires energy. And then, in a liquid, the particles are touching. They're all stuck close together. However, in a gas, they're spread far apart. And so the energy required to boil it is the energy needed to separate those particles, to spread those particles away from one another. So lifting an object off the ground or pulling two magnets apart requires energy. We know that. We can feel it when we try. In the same way, particles in a solid require energy to overcome the forces of attraction that are holding them in fixed positions. And the particles in a liquid require energy to overcome the force of attraction holding them together. This energy is supplied by heating. Figure B shows how increasing the energy in a material changes the arrangement of the particles. So the important thing to recognize here is that thermal energy is all due to the particles vibrating, whereas internal energy is both the particles vibrating plus the energy needed to break those bonds. That is the potential energy. So here we have an equation which tells us the specific latent heat for different materials. Now, we have two different versions of specific latent heat, but they're essentially the same. One is fusion, that is to melt something, and one is vaporization, that is to turn something from liquid to gas. Now, the reason they're put on here separately, even though they're essentially the same equation, is because for materials, they aren't always the same number. The energy required to turn 1 kilogram of ice into 1 kilogram of water is not going to be the same energy as the energy required to turn 1 kilogram of water into 1 kilogram of water vapor or steam. So let's apply this equation now. Here we have calculating the specific latent heat. So 300 joules of energy is needed to melt 0.075 kilograms of a material. Calculate the specific latent heat of fusion for this material. So step 1, you should write down what it is you already know. We know energy and we know mass. Step 2 is to write down the equation we're going to use. Specific latent heat equals energy divided by mass. Step 3 is to plug in those numbers. And step 4 is to write the answer with correct units. Next, 1000 joules of energy is needed to melt 5 kilograms of the material. Calculate the specific latent heat of fusion for this material. So again, the first step is to write down what we know. The second step is to write down the equation. Third step is to plug those numbers in, so substitute the numbers. And step 4 is to write the answer with correct units. Copy this down and complete the missing step. "12 kilojoules of energy is needed to melt 3 kilograms of material. Calculate the specific latent heat of fusion." This time, the energy, because it's 12 kilojoules, we need to convert it to SI units, so it's 12,000 joules of energy. The mass is 3 kilograms. The next step is to write the equation. Step 3 is to substitute in the numbers, and 4 is to write down our answer with correct units. Copy down the two steps shown and include steps 3 and 4 yourselves. "75 kilojoules of energy is needed to melt 5 kilograms of material. Calculate the specific latent heat of fusion." Pause the video so you can copy step 1 and complete steps 2, 3, and 4. Finally, 4 kilojoules of energy is needed to melt 8 kilograms of material. Calculate the specific latent heat of fusion for this material. Complete steps 1 to 4 yourselves. Pause the video if you need time. Next, calculating the energy required. So let's say we have 8 kilograms of mass. We know that it has 400 joules per kilogram in order to vaporize a single kilogram. So 400 joules is required for each kilogram. Calculate the energy required to vaporize it. So the first step is write down what we know. We know that L is 400 joules per kilogram and M is 8 kilograms. Second step is to write down the equation. L equals E over M. Third step is to put the numbers in. So instead of L, I write 400, and instead of M, I write 8. Meanwhile, E remains the same. And then I'm going to make E the subject of the formula. Now, since it's E divided by 8, what I'm going to do is the inverse operation. So I'm going to make the other side multiplied by 8. And this gives us an answer of the energy required to melt it is 3,200 joules. Sorry, not to melt it, this is to vaporize it. Next, a 2 kilogram mass has a specific latent heat of vaporization of 50 joules per kilogram. Calculate the energy required to vaporize it. Copy down steps 1 to 4 and complete step 5 yourselves. An 8 kilogram mass has a specific latent heat of vaporization of 20,000 joules per kilogram. Calculate the energy required to vaporize it. Copy down steps 1 to 3 and complete steps 4 and 5. A 7 kilogram mass has a specific latent heat of vaporization of 150 joules per kilogram. Calculate the energy required to vaporize it. Step 1, write down what you know. Step 2, write the equation. Step 3, substitute in the numbers. Step 4, make E the subject of the formula. And step 5, give your answer with correct units. Copy down the steps shown and complete the rest. A 6 kilogram mass has a specific latent heat of vaporization of 1,200 joules per kilogram. Calculate the energy required to vaporize it. Complete steps 1 to 5 yourselves. Now, what if we know the specific latent heat and we also know the energy supplied? This could tell us the mass of the material that we have. So, a material with a specific latent heat of fusion of 400 joules per kilogram is melted completely by 20 joules of energy transferred to its thermal store. Calculate the mass of this material. Step 1. Write down what we know. We know the specific latent heat of fusion and we also know the energy. Step 2 is to write down our equation. Step 3 is to substitute in the numbers. Now this time it's 400 equals 20 divided by m. So I'm going to have to do 2 steps in this operation to move it. First of all, I'm going to put m on the left hand side. So because it's 20 divided by m, I'm going to times both sides by m. So we'd end up with 400m equals 20. Then I'm going to, since it's m times 400, I'm going to divide both sides by 400. So therefore m equals 20 divided by 400. And finally, write down the answer with correct units. Copy down these steps. A material with a specific latent heat of fusion of 5,000 joules per kilogram is melted completely by 8,000 joules of energy. This time, again, we write down what we know. Then we write down the equation. We substitute in the numbers. Then we make m the subject of the formula. And then finally, step 5, write down the answer with correct units. Copy steps 1 to 4 and complete step 5. A material with a specific latent heat of fusion of 1,100 joules per kilogram is melted completely by 13.2 kilojoules of energy transferred to its thermal store. Calculate the mass of this material. So this time, we'll need to convert the energy into SI units. So we know that 13.2 kilojoules is in fact 13,200 joules. So again, complete steps 1 to 3 and do steps 4 and 5 yourselves. So a material with a specific latent heat of fusion of 2,400 joules per kilogram is melted completely by 7.2 kilojoules of energy transferred to its thermal store. Calculate the mass of the material. Again, we've got kilojoules, so we're going to need to convert and copy steps 1 and 2 and complete steps 3 to 5. And finally, a material with a specific latent heat of fusion of 8,000 joules per kilogram is melted completely by 0.56 kilojoules of energy transferred to its thermal store. Calculate the mass of this material. Complete steps 1 to 5 yourselves. Now, if you're struggling to understand anything, you can read this textbook page I wrote and complete the questions given, as well as the following textbook page. This also has a number of calculations for you to practice.